Introduction. The purpose of this lab was to use magnets and a magnetometer to experimentally understand magnetic fields. We will also compare these results to the values predicted by the equations. Results. The on-axis magnetic field was double that of the perpendicular magnetic field. There is error between the experimental and computational fields, and the observed values for the experiment were an N of minus 2.902, a K of 5.9 times 10 to the power of minus 7, and a mu of 2.95. Fundamental principles. The main equations we used were the equation for the general magnetic field, which the magnetic field is equal to our magnetic constant times 1 over the distance vector's magnitude cubed, times 3 times the dot product of our magnetic moment times the unit vector of our distance, times the unit vector of our distance, again, minus the magnetic moment, as well as the equations given for the model in which the absolute value of our magnetic field is equal to the constant k times the r distance vector to the power of n, and ln of the same b field but only in the x direction is equal to the ln of our constant k plus n times the ln of our distance vector r. And the parallel magnetic field equation, B parallel equals our magnetic constant times 2 times the magnetic moment over our distance vector cubed. Well, the magnitude of our distance vector cubed. Lab setup. Our lab setup included a magnetometer and a bar magnet, in which the bar magnet was moved closer and farther from the magnetometer until the magnetometer had a certain B field reading in the x direction, at which point the meter stick was used to determine the distance between them. In this lab, the system was the magnetometer, while the surroundings was the bar magnet exerting the magnetic field on the magnetometer, as well as everything else, which includes Earth, which had the Earth's magnetic field exerted on the magnetometer. Experimental results. Using our two equations from our fundamental principles slide, we can tell that kr to the power of n is equal to mu naught over 4 pi times 2 times mu over r to the power of 3. Since n about equals negative 3, then mu equals k over 2 times mu naught over 4 pi. Therefore, k is equal to and using our value of k equals 5.9 times 10 to the minus 7, we can then calculate mu to be 2.95. Also, using our calculations from the actual experiment, we know that the B of the off-axis magnetic field is 4.03 e to the minus 5 in the x direction, 2.21 e to the minus 5 in the y direction, and negative 2.47 e to the minus 5 in the z direction. Computational results. Basically, my code creates a magnet at the origin and uses the magnitude of the magnetic moment from the experimental results and a function to find the B field due to the dipole of the magnet at any observation location, and then creates multiple arrows to express the magnetic field at multiple different observation locations, both on axis and perpendicular to the axis of the magnet. It then uses the distance perpendicular from the experiment and the same function to determine the computational results for the magnetic field at the distance at a 45-degree angle, which is found to be 6.92 times 10 to the minus 6 in the x direction and 2.08 times 10 to the minus 5 in the y direction and 0 in the z direction. Our experiment has plenty of error. This is mostly due to magnetic interference around our magnetometer, as well as human error and the inaccuracy of the magnetometer. What if you hadn't oriented your experiment to compensate for magnetic north? If this happened, then the magnetic field due to the Earth would not be perpendicular to our Bx vector. Therefore, it would interfere with our readings for B of x and would create catastrophic error in our computations and experiments. If two identical magnets were stuck together end to end, the law of superposition would create a larger magnitude for the B field. In conclusion, there is a large difference between our experimental B off axis vector and our computational B off axis vector.